I'm gonna talk about higher geometry, introduce higher geometry, give a vague definition, but I'm going to restrict myself to the easiest example of generalization of principal bundles, namely a strict principal two bundles. This is the first generalization of principal bundles, which characterize gauge theories, as we know. So at the end of the talk, I'm going to talk about fake flatness. Fake flatness is the root of skepticism against higher gauge theory. Uh, this is because of a lack of good definition for connections. Uh, but there is progress, and there's a good progress in that regard. So I'm going to talk about at least how we should formalize this locally and address fake flatness uh, to give a consistent higher gauge theory. And at the end, I give a very interesting example of how you imply this theory, the very interesting uh, theory, which is Lie algebroids. I'm gonna talk about these things. Okay. Okay. So let me introduce Lie groupoids. So a Lie groupoid consists of two smooth manifolds with a bunch of smooth maps between them, subject to some conditions, which looks very like a group. That's why we call them Lie groupoids. You can also lift the notion of action of a Lie group to actions of Lie groupoids, and morphisms of Lie groupoids are defined as bibundles, and we have again morphisms between bibundles, which are called two morphisms. And it's a classic theorem that Lie groupoids and bibundles form a bicategory. Uh, so we take this bicategory and we want to talk about interesting things about them. The first interesting thing is that in classical geometry, we know that given a Lie group, the classifying space is a very complicated space, infinite dimensional, and so on. But you can prove in a sentence that given a Lie group, the classifying space is simply given by a Lie group, which does not have, so the M so the M in this definition is just a trivial manifold. You can prove that, so more precisely, you can prove that the category of principal G bundles on a manifold X is equivalent to bibundles from X to BG. You can prove this kind of in a sentence. uh, let's give more interesting things. So in physics and also in mathematics, we are interested in singular spaces, which are the quotient spaces, like orbifolds or a quotient of a manifold by an action of a group. So these spaces can be thought as a Lie groupoid. For example, if you have an action of a Lie group G on a manifold X, you can prove that the corresponding Lie groupoid has all this universal property that you expect for a quotient. For a, a very interesting example is that you take the uh, principal given a group G, in physics, you want to think about principal G bundles with connections, which characterize your gauge theory, right? And you want to think about them up to gauge transformations. So instead of taking the quotients by gauge transformations, you can think about the corresponding Lie groupoids. And indeed, that Lie groupoid differentiates to the BRST formulation of gauge theory. So in a sense, this higher geometry objects integrates BRST or BV. So they integrate perturbative field theory to a non-perturbative one. And another example are orbifolds, which are proof that there are special kinds of Lie groupoids. Okay, now with these motivations, we want to move to give a little taste about the physics side. So in the physics, we only see things infinitesimally or perturbatively. So in physics, we see the linearization form of higher geometry. The linearization of higher geometries are L-infinity algebras. So, or more generally, L-infinity algebroids or differential graded manifolds. They're the same concept. Okay, here is the definition of L-infinity algebra, but we don't really care about the definition at the moment. So the first appearance of L-infinity algebras was in the work of Zuybach on closed string field theory. Zuybach showed that string amplitudes can be written in terms of some functions which satisfy some identities. And those functions and those identities just define an L-infinity algebra. This is the first encounter of physicists with L-infinity algebras. But there are more. If you don't want to think about fancy things. So as a particle, we know in a standard model that a particle can couple to a one form through its word line. So in the same way, closed strings can couple with the two form through their word sheet. This is the classical B field that we are interested in string theory. And it is also showed that for this theory to be anomaly free, it has to be really a connection on higher principal bundles. So it's really a higher gauge theory. So with this in mind, you wouldn't be surprised that this B field and higher gauge theory also appear in supergravities, as supergravities are low and low energy limit of M theory or string theory. So people knew for a long time that in Young-Mills supergravities, the one form potential A and the two form potential B coupled through the three form curvature. This is a very old result. And so these two together have an underlying Lie2 algebra, which is a specific kind of L-infinity algebra. And indeed, this Lie2 algebra is lifted to or integrated to a Lie2 group, which is usually called a string 2 group, which is also very has many interesting things, but I don't really want to talk more about it. The other interesting example is M theory. So in M theory, it is postulated by Witten that that the theory of interacting membranes are given by a theory which is called the 2,0 theory. And also by Witten, along with many others, it's argued that it, there are arguments against existence of this theory at Lagrangian level. So people believe that this is a completely quantum theory which does not have a classical limit and Lagrangian. So the root of all these arguments, the important argument against the existence is in higher gauge theory, because people think that there's no consistent theory of higher gauge theory or connections on higher principal bundles. The reason that we know that this must be a higher gauge theory is that in the analog of a string theory, if you want to think about brains, we know that strings end at brains, and the endpoints characterize your particles. In the similar way, M2 brains end at M5 brains, and the endpoint, we don't have endpoints, it's an end line, so it's a higher dimensional object, so it should interact with the 2,4. So we know that it must be a higher gauge theory. But with the recent developments, people have come with a good notion of higher gauge theory, and they indeed have a candidate for describing M5 brains. This is not the final thing. It's just a candidate that have passed many tests. Okay. This was the motivation part. Now I want to introduce higher geometry. Okay, to introduce higher geometry, I want to first introduce infinity categories. To give you a taste what we're looking for, think about a topological space X. We want to form a category out of this space. So the category that we are interested in has the objects are the points in your topological space, and morphisms are paths between these points. But we know that we have to consider paths up to homotopy for this to be consistent. But considering paths up to homotopy is not the most natural thing to do. The more natural thing to do is that is because homotopies are actually paths between paths. So it should be a morphism between morphisms. So the idea, so this is the idea of definition of infinity categories. So in other words, infinity categories are trying to resolve homotopy theory or homotopy categories. That you in homotopy categories you want to quotient morphisms, but we now want to resolve this. This not only resolve homotopy category, also have more informations. The homotopy category only considers in homotopical category you only get the first fundamental group, but in infinity category, you get all the fundamental groups. So it has a lot more information for you. So the definition of so with this in mind, the definition of infinity one categories, to be precise, is a category enriched over infinity groupoids, because we want to resolve homotopy category. So roughly speaking, between two objects, we do not have the set of morphism. Instead, we replace it with the infinity groupoids. And in fact, infinity groupoids are defined such that they are the same concept as topological spaces. There are various models for infinity groupoids, but all of them are invariant. So we don't really want to pick pick one model for infinity groupoids. So this is the idea of infinity categories. Now, how do we think about infinity geometries or higher geometries? To see that, I want you to think about sheaves. A sheaf is a contravariant functor from a category to the category of sets. Now, we understood that it's more interesting to replace sets with infinity groupoids. This is called an infinite sheaf. From the other way, we understood that Lie groupoids are very interesting. And indeed, it is proved that Lie groupoids are a higher geometry. Lie groupoids are the same as differentiable stacks, which is a two-sheaf. So the generalization to infinity geometries or generalized higher geometries is to talk about differentiable infinity sheaves. This is the definition of Lie infinity groupoids, but we don't really want to talk about them because they're fancy mathematics. We want to just focus on easy things. So a general theory of principal infinity bundles is developed, but we want to focus on the easiest example, which is a strict principal two bundles. Now I want to give the strict definition, the exact definition, and do not think about infinity things anymore. So as you may expect, uh, first we have to define Lie2 groups, a strict Lie2 groups. So a strict Lie2 group is replacing sets with groupoids. So a strict Lie2 group is a Lie groupoid together with a composition functor, inverse functor, and identity functor, which satisfy the obvious and evident conditions that you think for groups. We can also define a strict action, which is the obvious thing that you may expect. So to make it more precise, to make it more obvious that what these spaces are, it is proved that a strict Lie2 group is equivalent to cross modules of Lie groups. So in other words, a strict Lie2 group is given by a pair of groups, namely G and H, with a homomorphism from H to G, and an action of G on H by an automorphism, subject to these conditions. So for strict Lie2 groups, you need this information. Now, we understood Lie2 groups. We want to talk about principal bundles. So as again you may expect, we replace sets with groupoids. A strict principal 2 bundle becomes over a manifold M. We restrict ourselves to the case that the bundle is over a manifold, just for simplicity. So a strict principal bundle over manifold is a Lie group with a surjective submersion to M, which is respected by right action of your Lie2 group G, curly G. And the morphisms of principal bundles are given by an equivalent bibundle. So uh, we don't, I don't really give the notion of equivalent bibundle here, but this is what you may imagine. So again, we can make it more precise. We can make it more apparent that what is really a principal 2 bundle. First of all, I want to mention that in the same way that the classifying space of a Lie group is a Lie groupoid, you can also give the classifying space of a Lie2 group by Lie2 groupoid. But this is just just a comment. But now, as principal bundles are uniquely determined by cocycle over a cover, this is also true for a strict principal 2 bundles. So to know a strict principal 2 bundle, you need a cover and generalized cocycles. So you need maps Gij from the intersection of Ui and Uj to G, which is similar to the usual cocycle. But also you need a map H to Hij from intersection of three open sets to H, and they satisfy these relations. This is indeed the zero non-abelian cohomology. And so if you want to if you're already familiar with U1 gerbs, a U1 gerb is the case when you put G to a trivial group and you take H to be U1. This becomes a U1 gerb. Okay, now that we gave the topological part of higher principal bundles, we want to talk about their connections. I don't give the global definitions because it becomes a little complicated. So I want to only talk about in the local case, such that the topological part is trivial. Okay. So first, I want to talk about the problem that we have in our definitions. So first of all, indeed, the principal infinity bundles is defined and the definitions are settled, and we are very happy with them. But the notion of connection is more subtle to define, and there is debate on them in the literature, and people, for example, me, we are working still on them. And all of the definitions which are in the literature suffer from fake flatness. So what is the fake flatness in the easiest case? So in a two-gauge theory, two-gauge theory is given by one form potential and a two-form potential. And we have a two-form curvature and a three-form curvature. So the fake flatness is that the two-form curvature must be zero for all the gauge transformations and so on become consistent. But this is not natural at all because, first of all, you want to think a gauge theory trivially as a two-gauge theory. But this is not true anymore because the two-form curvature must be zero and it becomes a flat connection. Indeed, there is more problem with this fake flatness because it tells you that locally you can gauge away the one form, and many interesting examples that we know in physics, especially in supergravities and M theory, they do not have this property. So we need the one form. So this is not the definitions in the literature are no good. But to give a very good definition, I want to introduce differential graded manifolds. People, you can easily see that differential graded manifolds are the correct notion to define connections because differential graded manifolds are the infinitesimal version of higher geometry. So you can, in the same way that you can differentiate a Lie group to a Lie algebra, you can differentiate a higher geometry to differential graded manifolds. So you have to replace Lie algebras with differential graded manifolds, or in many cases, the manifold part is trivial. So in that case, it becomes just an L infinity algebra. So the definition of graded manifold is the following. A graded manifold M is a sheaf of local rings such that the local rings looks like this algebra, or we usually say that it's modeled on this algebra. Okay, an important example is the shifted tangent bundle, or probably more in classical geometry, people would say cotangent bundle, but we call it a shifted tangent bundle because we want to see the forms as the algebra of functions. So the shifted tangent bundle is defined by putting the topological space M to be the topological part of your manifold and put the algebra of functions to be the algebra of differential forms. And a differential graded manifold is just a graded manifold with a differential on the algebra of functions. Okay. Now, how do we give an L infinity algebra? How do we define a connection locally? So, given a manifold X, we can define a connection, a local connection, to be just a map of graded manifolds T1x to G. As I told you, L infinity algebras, or more generally, L infinity algebroids, are the same as differential graded manifolds. They're the same notion, and I use the name interchangeably. So a local connection is nothing but a graded map from T1x to G. Equivalently, you can prove that instead of having a graded manifold, a graded map from T1x to G, you can think about differential graded maps from T1 to T1G. So a differential graded map must also respect the differential, and the differential is kind of absorbed in the T1 part of T1G. But how do we define gauge transformations? So gauge transformations are given by similar constructions in a case set. So as we want to define here. So here we want to give you the BRSTs. At first, I want to talk about the flat BRST. The flat BRST is exactly given by AKS set. So given an L-infinity algebra, G, and a manifold, the flat BRST is the representation of some presheaf. So the presheaf is a map, is a functor, is a contravariant functor from NQ manifolds to sets. NQ manifolds are just differential graded manifolds concentrated at positive degrees. The reason to think about NQ manifolds is that we are thinking about BRST. If you put DG manifolds, you think about BV. So because we are interested just in BRST, we think about NQ manifolds. And the presheaf is given by this map. So an NQ manifold X is mapped to the set of maps from X time T1M to G. This is the classical AK set. So, but you only get flat connections because we are in the category of DG manifolds and all maps must respect the differential. And in the case of G being Lie algebra, you get exactly the BRST that you have in physics, but flat BRST that you have in physics. For Lie2 algebras, this is also calculated. You can see the paper by Simon and Schmidt. Now we want to talk about non-flat case. So there is a theorem saying that there is a bijection between graded maps from X to G and differential graded maps from X to T1G. So the first step is to replace G with T1G. But this makes the target space much bigger to accommodate a non-flat connection. But so it also introduces more gauge transformations. So there are also gauge transformations associated to curvatures, but we don't want that. We want to restrict gauge transformation. To do that, you first need a notion of curvature. So we define an adjustment datum to be a decomposition of T1G with G and another space G bar, right? So G describes the connections and G bar describe curvatures. So this decomposition is known as adjustment datum in the literature. Now we want to define a full BRST. So given an L-infinity algebra and an adjustment datum or decomposition of T1G, we define a presheaf on NQ manifolds that send an NQ manifold X to the set of maps F from X time T1M to T1G. But we want to restrict gauge transformations. The restriction is by assuming this commutative diagram. in this diagram, F bar describes curvatures for you. The map from kind of in the representation form, it talk about maps from T1M to G bar, which describes curvatures. And the absolute value of x, by absolute value of x here, I meant the underlying manifold. I will show you that how this restrict gauge transformations. So the full BRST is representation of this functor. This functor is a presheaf. So we already know that how people construct AKZ or the representations of these presheafs. So the space BRST of MG is given by maps of different degrees. So to give the full to get the full BRST, instead of considering only maps that respect degrees from T1M to T1G, you think about maps of different degrees. So the degree 1 elements, the maps of degree 1, describes gauge transformations, and maps of degree 2 describe gauge transformations of gauge transformations. Now, this commutative diagram translates to this condition that if you compose F with the projection to bar G, it's a degree 0 map. In other words, the curvature must be degree 0. So there is no gauge transformations associated to curvatures. But in many cases, if you don't consider a good decomposition here, the adjustment datum, this condition can produce more conditions for you because it has to be compatible with the differentials of T1M and T1G because it's a differential graded map. It produces more conditions if you don't choose a good decomposition, and this is known as fake flatness. Okay, now I want to give a few remarks about these definitions. First of all, if G is just a Lie algebra, the T1G has a unique decomposition. This is a degree reason because L infinity, if G is a Lie algebra, it only has degree 1 element, the connection 1, 4, right? And G bar is the connection, is the curvature, which is a 2, 4. And there is no way that you can mix them. There's a unique decomposition. And I also talk about fake flatness, which arises when a suitable decomposition is not chosen. And the other thing is that the representation of this BRST is calculated for some Lie-2 algebras which are interested in constructing M5 theory. So at least the local description of the candidate for M5 theory is calculated. But the example that I want to talk about is Lie algebroid, the case that G is a Lie algebroid. Why is this example interesting to us? The reason is that Lie algebroids describe gauged sigma models. So we also know that a standard model is a gauged sigma model, at least if you don't think about the spinor part, it's just a gauge sigma model. So because of that, the algebraic gauge theory is interesting to us. In the case of a standard model, of course, the target manifold is just Rn, but in general case, the target manifold can be a very non-trivial space. So how do we what is the result of applying these definitions to Lie algebra? If you take a Lie algebra G, which is defined on a manifold X, it is proved that a Lie algebraic connection nabla induce a decomposition of T1G to G plus something else, which we think about the rest as curvature. And we can it's easy to show that the degree 0 elements of BRST or the connections are just a pair phi and A, where phi is a map from your space-time M to X. This is the sigma model part. And A is a F star G value differential form. So it's somehow the generalization of is a vector value differential form locally, but for considering the topological part, it's really an F star G value differential form. The one form curvature is also given by d phi minus rho of A. Rho here is the anchor map of your Lie algebra. And the connection 2, 4 is also given by this equation. Here the omega are the coefficients of your Lie algebraic connection nabla. Now, what are the gauge transformations? The gauge transformations are given by, again, infinitesimal gauge transformations are given by vector valued functions or F star G valued functions on your space-time manifold M, and the gauge transformations are given for the gauge transformations to close, or in other words, for the BRST, the QBRST to be nilpotent, either the one-form curvature should vanish, or nabla must be a Cartan connection. So you see that if you do not choose a good decomposition, which in this case is given by nabla, you get the fake flatness condition, which is the connection one form to be 0, right? So this is an example of how you should apply this. What is the result of applying these definitions to at least the Lie algebraic case? And this can describe a gauge sigma model for you in a more mathematical, consistent way. Of course, this is just a local definition. The global definitions, instead of talking about Lie algebraics, you have to talk about Lie groupoids. But I didn't really want to talk about the global case as we didn't have time and it's much more complicated. Yes, so that's all I wanted to tell you. And oh, there was a typo in attention.
Thank you very much.
Yeah, I'm very happy that I had this opportunity, and I hope that I inspired you to think about higher gauge theory more.
Most definitely. Thank you very much. So. I think your talk sparked many questions in the audience, so let's unmute
Should
yourself.
I again share my
Yeah.
crowd? Okay.
So, questions?
At the beginning, hi, Mehran.
Hi.
At the beginning, you mentioned, concerning the physics, that we concentrate on singular quotient spaces. Why is this case? Why we concentrate on singular quotient spaces in gauge theories? Or
You mean this statement?
yeah.
Yeah. So in first of all, in gauge theories, for example, we are interested in connections on principal G bundles, but up to gauge transformations. So this is a quotient space, and you don't know if the quotient is a manifold or not, because the action of gauge transformations is not necessarily a proper action. So you cannot define the quotient space. But if you think about Lie groupoids, you can. So in other words, the quotient space uh, is probably singular, right?
Okay.
Maybe we have problems with connection, not higher gauge, but internet. Mehran, can you hear me?
Sure, yes.
Yeah, because you somehow run from our viewpoint. But if you do hear me, we can continue with the questions.
Yes, sure. Yes, I can hear you properly.
Is there any question?
So you mentioned this fake flatness, right? So, and you said that for fake flatness, you need to have a suitable decomposition. So could you say again, like, what exactly do you want from this decomposition? Like, it should be, like, how good or how suitable it should be?
Yeah, so that's a good question. So in the okay, in the case of Lie-2 algebras, the people know that what this decomposition should look like. It's given by a vector valued function, and we know that what this should look like. But generally, I would say that it should be nice enough that you can, such that the representation of this pre-shift exists, right? So because if so if the decomposition is nice enough, you don't get further constraints uh, on this construction of this AKZ construction. So it gives a representation of your pre-shift. But if there are more, if the, if you get additional conditions, additional consistent conditions, then you don't get the representation. So as far as the representation of the BRST pre-sheaf exists, I guess it defines a consistent gauge theory for you, and it depends on your application if you're happy with the final representation or not.
I see. Thanks.
Maybe I would have a question about the BRST. As far as I know, we can put higher homotopies along the computations of mapping between cylinders and the target object. So, according to this logic, I would expect you can obtain only gauge transformation, but not higher ones. Can you explain me maybe in more detail how one can obtain even higher gauge transformations and stuff by your construction?
Yeah, so in this construction, we consider maps of different degrees from your space-time manifold to T1G. So the degree 0 part is the connection.
Mm-hmm.
The degree 1 part is gauge transformations, and the degree 2 part is gauge of gauge, and it goes to infinity, right?
Okay.
And it depends. So if your L infinity algebra G is concentrated at degree 1, you can only expect for degree 1 maps, because there's no other uh, there's there's no other generator that you can map to, right? But if your L infinity algebra is concentrated at degree 1 and 2, you get you can get uh, degree 1 maps and degree 2 maps, and the degree 2 maps are gauge of gauge.
Mm-hmm. Mm-hmm. I see.
So I guess your point of view is more like the flat homotopies, right?
Mm-hmm.
So we know that I know that in the examples it becomes the same as the flat homotopies that people also consider, uh, but I don't know the details that why they're equal.
Mm-hmm. And could you somehow rephrase the same logic from Lie algebroids to Lie groupoids? So you're
For
not considering
this example,
um, for the case of construction of BRST, right?
yes.
If you can reconstruct this right way from groupoidal settings.
Oh, you mean the global picture of
Yes, yeah.
algebra? Yes. So the global picture in the global picture is difficult, but the thing is that so you, in this in the similar way that you have the classifying space of Lie group, the classifying space of Lie groupoids are themselves.
Mm-hmm.
So you can think of principal groupoid bundles.
Mm-hmm.
So the gauge group is replaced by a groupoid. So you can shift this. Let me. Yes. So in that case, a principal Lie groupoid bundle is a manifold with a surjection submersion to M and a right action of your Lie groupoid such that the so-called shear map is an equivalence. Right.
Okay.
So in the same way that P, if you think about the quotient of P with your right action, you get your manifold. Right. This is the topological definition of principal Lie groupoid bundles. And the connection is given by the connection is you can give it again by classifying spaces, which is given by the generalized Chevreul differentiation. So the classifying space is given by again some representation, but the representation is in the category of DG Lie groupoids. It's a groupoid internal to differential graded manifolds.
Oh.
And this is given by again the Chevreul differentiation. The generalized Chevreul differentiation. If you put your Lie groupoid in that definition, it produces a groupoid internal to DG manifolds, and that space describe the classifying space of your flat connections. Again, to get non-flat connections, you have to extend this the similar way that we extend G to T1G with some obvious constraints and so on. But it becomes a little more complicated. But you can think about them again in the classifying space. But the classifying space is given by DG Lie groupoids.
Yeah. The source of my question arises from the concept of gauge transformations, which you can define in a groupoidal setting as well. So it was very interesting. Thanks. Any other question? So, if not, I would like to thank to you again.
Thanks for the invitation.
Thanks very much, and we have to discuss maybe later about this.
Sure. Thank you very much.
Bye.
Bye.
Thank you.